All right, our last speaker today is Andreas, who will talk about package management integration with Bazel. That's a topic that's dear to my heart. Take it away.
Thank you. My name is Andreas. I work for Tweag.io. We are a Bazel community expert, one of the first Bazel adopters, and developer of new features and extensions. I assume everyone here knows about Bazel. One of the great features of Bazel is its support for multi-language development. So you can define targets written in many different languages, combine them together, build them all with a single command, and extend Bazel to support new languages. This all works great as long as the sources are within the same repository. But what about external dependencies? Most languages come with rich third-party library ecosystems. Many languages come with existing package managers dedicated to those languages with features like dependency resolution, version compatibility, and so on. Can we make use of those within Bazel? Oops, there. So to set the stage, I'm going to demonstrate 3 different ways how you could handle external dependencies. The first is to just vendor those dependencies. So you just copy the source into your repository, define custom Bazel targets for those. This is a very flexible approach, but it can have a very high maintenance cost, especially if you want to do updates of your dependencies and such. Another way is to automatically generate Bazel targets. So you have some way of parsing the package definitions of your external dependencies, and then you automatically generate Bazel targets for those for the rule set for your language of choice. And this is automatic, so it has a lower maintenance burden on updates and such, but it can be a lot of effort to implement the tool that does this automatic generation, depending on how complex package definitions in your language are. So the third approach, and what we think is the best if possible, is to just integrate the existing package manager for that language into Bazel. So you just call out to the package manager to do dependency resolution, version resolution, and builds if necessary. This is automatic, so updates are very low maintenance. It's very compatible. Your package manager should work with most packages out there in that language. A downside can be that the dependency graph this generates could be more coarse-grained than what you might define manually, so you could lose out on some build parallelism. So let me introduce Rules Haskell. At Tweag, we developed Rules Haskell as a Bazel extension for Haskell. For those who don't know, it's a strongly typed, purely functional, lazily evaluated general-purpose programming language. Historically, we used to use the second approach from the previous slide. So we parsed the package definitions for Haskell dependencies. We then generated regular Rules Haskell library binary targets. But we found that it is very difficult to emulate all the things the package manager does with an implementation in Bazel, especially when it comes to supporting Linux, macOS, and Windows simultaneously. So what we do now is to integrate with the existing package manager. There are 2 tools that are important here. One is Cabal, and the other one is Stack. For the purposes of this talk, Cabal is the Haskell build system we use to build external packages, and Stack is the package manager that we use to do version resolution, dependency resolution, and fetching of external sources. Users interact with this with 2 different components. One is Cabal rules. These are build rules that call out to the Cabal build system to build third-party packages, or any Cabal packages, really. These are regular build rules, so you can use them in any build file. So you could use this for vendored packages or legacy packages. And it integrates with the regular rules, Haskell library and Haskell binary. And then the second interface is the repository rule stack snapshot, where we call out to the Stack package manager to do resolution of dependencies and versions and fetching those external sources. And then this is a repository rule, so it defines Bazel, it generates build files with Bazel targets in them, generating these Cabal rule targets that I showed before. If you're familiar with rules JVM external, this is somewhat similar. And yeah, an use case example is on the right side of the slide. So you can also introduce C library dependencies. Stack has curated lists of compatible versions. You can pick the snapshot that you want to use. For an example of what a dependency graph might look like. This is a subset of the dependency graph generated from the call on the right side of the slide. Pros to this approach, we are using the existing package manager infrastructure for the Haskell ecosystem. So this is very compatible. Most packages should work with this. And it's relatively low maintenance burden because all these package manager tools are already implemented. The dependency graph on the level of packages is still visible to Bazel, so Bazel can do parallelization and caching and all those things on that level. But of course, it's more, well, it can be more coarse-grained than what you might write by hand, so you're potentially losing out on some build parallelism. But we find that for third-party Haskell dependencies, at least this is a good trade-off. So finally, our key insights in this: if the package manager for your language can be made to avoid global state, then it can be called in a build action just like any other build tool, like the compiler or something else. And we find that the most efficient way to integrate with the existing library ecosystem for your language of choice is to just wrap the existing package manager into Bazel instead of trying to re-implement it within Bazel. Yeah, that's all I had to say. If you're interested in any of the rule sets we're implementing, that's rules Haskell, rules Nix packages, and rules SH. And also check out haskell.build and tweag.io. Thanks.
So one con that stands out to me is that if you have very large external dependencies, then when you update one of them or change one of them, then you invalidate the whole external repository. And like, have you actually done this with hundreds of external dependencies? What are the trade-offs that you see there?
So the question is, what about very large sets of external dependencies? If you change a dependency in there, you're going to invalidate a lot of targets and rebuild them, and how do we deal with this? So we have use cases with, I don't know the exact number, but on the order of 100 dependencies. And I mean, the problem exists either way, really. Like if you change a package deep in the dependency graph of your external dependencies, you're going to have to rebuild it in some form.
If it's not deep, then
yeah,
you're bundling up stuff.
No, but I mean, those generate regular Bazel targets. The Haskell Cabal library is a regular Bazel rule, so all the regular caching and everything applies. So if you only change something at the leaf of the dependency graph, it's not going to rebuild anything else. Yeah, so that works.
Maybe you mentioned it. What's the idea behind rules SH?
Right, I didn't mention that. So that's a fairly recent thing we did. There was a discussion on the issue tracker of Bazel Skylab about this. It's a tool chain for POSIX, like standard shell tools. And especially for this work, Haskell allows custom build scripts. So you can have packages which call out to AutoTools configure files and stuff like that. And if we want to do this in regular build actions, then we somehow need these standard shell tools available for configure to find. So with rules SH, we defined a tool chain that wraps the standard shell tools. Currently, it assumes that they are installed globally somewhere, so it gives you just a list of paths and then generates a path environment variable that is passed on to the configure script, and then it just works.
Do we trim unused dependencies?
Pardon me?
Do we trim those unused dependencies?
The question is, do we trim unused dependencies? I mean, if none of the targets you're building depends transitively on a particular external library, it's not going to be built. The definition is still going to be there somewhere, but it's not going to be built.
Because it's manual? You apply manual tag or?
No, so the user interface to this is for the external packages you're using, you list the targets that you are directly depending on. And then we call out to stack, which generates the transitive dependency graph of Bazel targets. And then if in your actual build file somewhere you depend on, say in this example, servant, and you build this, then it's going to build all transitive dependencies that come through servant, but it's not going to build any dependency that is not in this transitive closure. Do we still?
Yeah, we still have time. Let's do one more question.
So how do you guarantee that the transitive dependency parameter based on this definition is fixed? because if you do it multiple times, the transitive dependency can change.
You mean the version of it?
Versions of
Right. So here we exploit actually a feature of Stack itself, which is that it has snapshots of pinned versions that are all compatible. So in the very bottom of this, it says LTS-13.8. What this is a long list of package versions, version numbers, that are known to work together. So this pins the versions of all the transitive dependencies you're going to use. And you can do manual overrides if you want to override a version or a vendor package or whatever. So that's flexible enough. Yeah.
Thank you very much.
Thanks again.
All right, ladies and gentlemen, that concludes our first day of BazelCon. Thank you for great talks and great participation. I really enjoyed it. I hope you did too. And we will have a reception there in the cafe area over there, lobby area, from 5:30 until 7:30. So the drinks, snacks, things like that. Welcome.